In this video, we're going to review ions. So just a quick recap. Remember that atoms are the smallest particle of an element, and atoms are made up of three smaller particles or subatomic particles. We have the protons with the +1 charge. We have the electrons that are in the shells there with the -1 charge, and we have the neutrons that are in the nucleus with the protons, but they have a 0 charge or no charge. Now, what I want you to understand is that in a neutral atom, an atom with overall no charge, the number of protons and number of electrons are equal. So, for example, in this neutral carbon atom, there's 6 positive charges, 6 protons which are positive, and there's also 6 negative charges, 6 electrons are negative. Since they're even in charge, they cancel out, and so overall we have 0 charge. And so that's for a neutral atom. And for the most part, when you're looking at the periodic table, that's going to represent the neutral atom. But an atom won't always be neutral. The goal of an atom is to become more stable, meaning less reactive. And the way it does that is by completing its valence shell. So if an atom has a complete valence shell, then it's more stable. Remember that the valence shell is the last shell of electrons, and any electrons on that valence shell are called valence electrons. So the electrons in the valence shell are called valence electrons. And it's those valence electrons that are really responsible for determining the chemical properties of an element. They're the ones that are going to be reacting or bonding during a chemical reaction. So an atom really has reached stability when it has a full valence shell, when it's like the noble gases. When an element has achieved a noble gas valence shell, we say that it has a noble gas configuration. So it's stable like the noble gases in group 18. Now, there's several ways that atoms can achieve stability, can have a full valence shell. They can do that by losing electrons, so they can lose electrons. They can gain electrons, and they can also share electrons to become more stable. And so it really depends on what type of element you're dealing with, what class, when it comes to determining if you're going to lose, gain, or share. So let's talk about the idea of losing and gaining. When an atom loses or gains electrons, the charge is going to change. It's no longer going to be neutral because now you're not going to have a balance of positive and negative anymore that are equal. So if an atom loses or gains electrons, it's going to become charged, and it could be either positive or negative. Anytime you have a charged atom, we call that an ion. So a charged atom is called an ion, and the way that it became an ion was by losing or gaining electrons. Metals will generally lose valence electrons to form positive ions. Now, a positive ion has a special name. It's called a cation. So remember the trick here? The T in cation looks like a plus. So a cation is a positive ion. It formed by the loss of electrons. Remember that electrons are negative. So if you lose electrons, you become more positive. Think of them like negative thoughts. If you have a lot of negative thoughts, you're a negative person, so to speak. But if you lose negative thoughts, you become a more positive person. So metals tend to do that. Metals will lose valence electrons and become positive. So let's take a look at this example over here. Here we have sodium. It's a metal. This is neutral. There's 11 protons, 11 electrons. And so you'll notice that it only has one valence electron. To get a full shell, there's a couple things it could do. It could gain 7 electrons to get 8 on this last shell, but it's easier to lose the 1 so that below it, now it's full. So it's easier to lose 1 than to gain 7. So sodium loses an electron and is now a positive ion. Because if you think about it, we have 11 protons there, and now we only have 10 electrons. So the positives win by 1 charge. So really to complete this drawing here, what we do is we put a little square bracket around it and put +1. You wouldn't need to put this dashed shell there. It's gone because the electron was removed. Now this electron that was removed, it didn't just disappear or float away in the thin air. What it did is it went to some other element that probably wanted to take an electron to fill its valence shell. So some elements will, rather than lose, they will gain valence electrons, and that's typically nonmetals. So nonmetals gain valence electrons, and when they gain valence electrons, they become negative. They become negative ions. And so the name for a negative ion is anion. And I usually remember that this is negative because the AN, I just think stands for a negative ion. So when you gain negative thoughts, you become more of a negative person. When you gain electrons, you become more negative. So if we look at this example here, we have fluorine. This is neutral fluorine with 9 protons and 9 electrons. Notice on its valence shell, there's 7 electrons, 7 valence electrons. So you ask yourself, is it easier to lose 7 and have the full one below, or just gain 1? Well, it's easier to gain this 1. And so that's what happens. Fluorine gains the 1. Now there's 9 protons, 10 electrons. The electrons win by 1. So we can put a little square bracket over here and put -1. So as you can probably guess, the electron that was lost by sodium probably went to the fluorine there. And then that's how they would form a compound with each other. They would transfer electrons and form a compound that way. So you have metal and a nonmetal there. So metals lose electrons to become positive ions called cations. Nonmetals gain electrons to become negative ions called anions. And either way, as you can see, now they have their full shell, which means they are more stable that way. One more thing that nonmetals can do, and we'll discuss this in more detail later, is nonmetals can also share. Metals typically don't share, but nonmetals do. So that's another way they can achieve stability. But our focus in this lesson is really going to be on the ions, metals losing, nonmetals gaining. So again, here we have our neutral atom. If you lose electrons, you become positive. That's called a cation. If you gain electrons, you become negative. That's called an anion. Here we can see a diagram illustrating that point. So we have a Bohr-Rutherford diagram here of sodium. This is its neutral sodium with the 1 valence electron there still. To become more stable, it's easier to lose 1 than to gain 7. So here is our Bohr-Rutherford diagram of a sodium ion. You can do the same thing with the Lewis dot structure. With the Lewis dot structure, you just represent the valence electron. So for a metal, when you draw its ion, it's just going to be the symbol with the brackets over here and the charge. Now the charge is determined by how many electrons are lost or gained. So if 1 electron is lost, it's just +1. If it was 2 electrons lost, it'd be +2, 3 lost, +3, for example. So as a symbol, if we want to write this down as a symbol, we would write down this is Na, the neutral Na, and for the symbol of sodium ion, I would put Na plus. If it was 2 plus, I'd put Mg2 plus, for example. So that's how you would write down the symbol of the neutral versus the ion. Here we can see the anion forming. So we have the neutral chlorine with our 7 valence electrons. It's easier to gain 1 over here than it is to lose 7. And so that's what happens here. We form the ion of chlorine. By gaining 1 electron, its charge is -1. So if I were to write out a symbol for this, it would be Cl, and then put negative there. You can put the 1 as well. We don't have to put it because usually 1 is implied, meaning we know it's there. If it was any other number, you'd have to put it -2, -3, so on and so forth. With Lewis dot diagrams, it's the same idea. Here's your chlorine. I'm just showing that an electron is being added to the chlorine. We're only looking at the valence electrons there. Once it's full now, we can put our square bracket over here and put our -1 there. And so that would be the Lewis dot diagram for the chlorine ion. One thing to notice, you might remember this from grade 10, For nonmetals, the ending changes when you get to the ion. So chlorine atom becomes chloride. You change the ending to IDE. For metals, it doesn't change. So if we go back, sodium atom is still the sodium ion. That's it. We don't call it sodiumide. For metals, when they become ions, they're named the same way. You do have to specify if you're talking, for example, say, well, the sodium ion versus sodium atom. But when it comes to the name of the non-metal ions, you do have to change the ending to IDE. So, for example, oxygen, that's a bit of an exception there, but still works out, would become oxide. Chlorine becomes chloride. Fluorine becomes fluoride. And so just remember that the non-metal ion name changes to IDE. That we'll review more when we do some naming. So we'll do a couple examples together. I'll do some Bohr-Rutherford diagrams of elements and also their ions. We'll also do Lewis dot diagrams as well. So we're going to draw the ion for magnesium. First, what I'm going to do is I'm going to draw the regular Bohr-Rutherford diagram for magnesium. So I'm just going to go to our periodic table. And from our periodic table, we know that there's 12 protons here and also 12 neutrons. And there'd be 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11 and 12. And so this is just regular magnesium, the neutral magnesium, I should say. And we want to draw the ion, so we have to determine what ion it will form. This picture here has the charge given to you, 2 plus. If we go to our periodic table, you'll see that some charges are given if there's multiple charges, and we'll discuss that later on. But you'll see that for many, charge is not given. So for magnesium, the charge is not given. So what you'd have to do is you'd have to figure out the number of valence electrons. So it's in group 2. There's 2 valence electrons. And you'd have to ask yourself, is it easier to lose 2 or gain 6? Well, it's easier to lose 2 than it is to gain 6. So we know our charge is going to be plus 2 since we're losing 2 electrons. So as you can see, if an atom has 3 or less valence electrons, it's going to lose those electrons to make a positive ion. So what we can do is we can redraw this. Proton number staying the same, neutron number staying the same. What's going to be different is that we're just getting rid of our last shell because we got rid of those 2 electrons there. So this is now going to be, the shell below it is going to be the final shell. To indicate that this is the charged one, we put a square bracket like this and put 2 plus over here because we got rid of these 2 electrons. They were given probably to some non-metal somewhere else. And so that's how you would draw the ion for magnesium. And you could represent it as Mg, 2 plus. Protons still the same as regular magnesium, as neutral magnesium, so are the neutrons. The only thing that's changed is we have 2 electrons less than before. So just to compare, we have 9 protons here, 9 electrons here. I shouldn't say 9, sorry, I meant 12. Let's erase that. So we have 12 protons, 12 neutrons, and 12 electrons. Whereas for magnesium 2 plus, we still have 12 protons, didn't change. Still have 12 neutrons, didn't change. But now we have 10 electrons. So you don't have to draw the whole diagram every single time to find out how many electrons the ion would have. You just have to find out the neutral number of electrons and then take away the number of electrons from the charge or add the number of electrons from the charge if it's negative. So here we have the magnesium ion. It's a cation because it's positive. Lewis dot diagrams are a little bit easier to do. So neutral magnesium, like this. 2 electrons to lose. So we're just going to put magnesium symbol in brackets, 2 plus. And that's how you would do that for the Lewis dot diagram of magnesium, or really any metal, most metals that we deal with. So now let's try to do another ion. We'll do nitrogen. So I'm going to draw the Bohr-Rutherford diagram for the nitrogen atom in its neutral form first. So we have 7 protons, 7 neutrons, and 7 electrons if it's neutral. 1, 2, 3, 4, 5. So this is just a regular or a neutral nitrogen. It has 7 protons, 7 electrons, and 7 neutrons. As you can see, there's 5 valence electrons. So you have to ask yourself, is it easier to lose 5 or gain 3 to get that full valence shell of 8? And so it's easier to gain 3 than it is to lose 5. So you won't, again, always have the charge given to you. So if we go to our periodic table, we would see that nitrogen is in group 15, which means it has 5 valence electrons. It's easier to gain the 3, 1, 2, 3, than it is to lose 5. So 1, 2, and then 3, 4, 5 to get to the end there. So much easier to gain 3 than it is to lose 5. So let's go back and draw that in. So now what we do is we draw the same number of protons, same number of neutrons. That's not changing. It's only electrons that are changing. Our first shell is the same there. It's really in our last shell that we're going to see a difference. So we have 1, 2, 3, 4, 1, 2, 3, 4, and then 5. I just copied it the same way that I had drawn it initially. And what I'm going to do is I'm going to add my additional electrons now. So you can add them as dots, but I'm going to put them as X's just to show you there. We're putting 3 so we can get to 8. And then we're going to put a bracket like this. And we get to 3 minus. And so this is an anion because it's a negative ion. Now here I called it the nitrogen ion. In reality, you'd rename this. You would call this not nitrogenide. This is one of those interesting ones. It's nitride. Nitride. So again, here you could do the symbol would be nitrogen 3 minus. You'd still have 7 protons. You'd still have 7 neutrons. But since you're 3 minus, what that means is that your neutral one had 7 electrons. So if you're 3 minus, what that means is you've added 3 electrons to that 7. So now we have 10 electrons. And then you could do the same thing for the Lewis dot diagram. 1, 2, 3, 4, 5. Easier to lose 3 than it is to easier to gain 3 than it is to lose 5. So let's do that. So 1, 2, 3, 4, 5, and then 1, 2, 3. Put your square brackets there, and we get 3 minus. You can pause the video and try this one out yourself. I'm going to do the Bohr-Rutherford diagram, and then I'll do the Lewis dot diagram. So we're just going to do this for the ion specifically. I'll go straight off. I'll do the neutral one first, then I'll do the ion. And then we'll answer the question about whether this is a cation or an anion. And hopefully you can try to remember what the name of the phosphorus ion is once you figure out if you have a cation or anion. So let's go ahead and do the neutral phosphorus first. So we have 15 protons, 16 neutrons. So regular phosphorus, that makes sense, 15 protons. There'd be 15 electrons as well if it's neutral. And then there'd be 16 neutrons because I did 31 minus 15. Now we can start placing our electrons. So 1, 2. This one's going to be full. I know that because there's 15 electrons total, and I can only place 10 on the first 2 shells altogether. And then one more shell here. 1, 2, 3, 4, 5. This is the neutral phosphorus. It's in group 15, so 5 valence electrons. Easier to gain 3 than it is to lose 5. So this is going to form a negative ion. Basically, I'm gaining 3. So essentially, we're going to have the same number of protons, but now I'm getting 3 electrons. So I'm going to have 18 electrons. Still the same number of neutrons, though. So it's going to be a negative ion, so it's an anion. And so I can go ahead and draw that in. So 15 protons, 16 neutrons. And I'm just going to go and do the same structure I had before, but I'm going to add those 3 electrons that I now have. So we have 1, 2, 3, 4, 5, and I'm going to put those extra electrons there as x's. And I'm going to put the square brackets here. Since I gained 3 electrons, it's 3 minus. And you can do the same thing for Lewis dot diagram. So you can pause the video and try first, of course. 1, 2, 3, 4, 5. And then for the ion, it would be 1, 2, 3, 4, 5. And then add your 3 electrons there to make it a total of 8. And then don't forget to do 3 minus. So phosphorus, since it's an ion that's negative, an anion, you would actually have to change its name. And so the name of phosphorus is phosphide. Phosphide. Another one that's not intuitive when you're changing the name, I'm just going to add that here, is sulfide. Sulfur becomes sulfide when you make an ion. Nitrogen, nitride, oxygen, oxide. Chlorine is pretty straightforward. IDE, chloride, fluoride, iodide, bromide. Another one that's not super intuitive, hydrogen, if it does become a negative ion, is called hydride. So hydrogen would become hydride. Again, we're going to review that when we go to the naming in more detail, but this is some review, so it should be coming back to you. So you should be able to fill in tables like this when you see charges given to you. You can pause this and try this yourself, but I'm going to take some up with you. So let's take a look at the first one here. So essentially, if you don't see a charge written on top of the symbol, then you know it's the neutral version. So for example, here there's no charge. So I'm just going to put that this is neutral, and I can just fill it out as normal. I would normally would. So atomic number 12, protons 12, and since it's neutral, there should be 12 electrons to make it neutral. Now in this case, we have Mg2 plus. So since there's a plus there, that means that it's an ion. Specifically, we lost electrons. It's positive. It's a cation. So what I would do is my atomic number is still 12. That's still at the bottom here. My number of protons is still 12. That's not changing. It's the electrons are changing. So you have to figure out, did you lose or gain? Well, you're positive, so you lost electrons. How many? Well, 2. So that would be 12 minus 2, which is 10 electrons now. So let's go ahead and try this one. Nitrogen, no charge there. We know this is a neutral one. Atomic number 7, proton 7, since it's neutral, 7. Okay, let's take a look at this. So here we're told we have an ion, and we're given the atomic number. So the atomic number is 7, which means we're dealing with nitrogen again. And the number of protons will be 7. That's not going to change. But we're dealing with the ion of nitrogen. So we have to go take a look at nitrogen in the periodic table. If you look at nitrogen, it is in group 15, 5 valence electrons, easier to gain 3 than to lose 5. So it's going to gain 3 electrons when it forms its ion to get a full charge, a full set of electrons. So we're gaining 3 electrons, which means that we're going to have electron 7 plus 3, 10. So our charge is going to be 3 minus, but everything else is going to be the same. We're going to put 14, 7 there. We're just putting that 3 minus to indicate we now have 10 electrons. Let's take a look here. We have fluorine. Let's write that out as a standard atomic notation. So fluorine like this, 19 there, and 9 over here. This is the ion form. What would the atomic number be? Well, 9, because that's at the bottom there. Number of protons, 9. But we have minus now, minus 1. So that means that we have gained 1 electron. So we have 10 electrons. And that makes sense. These ones here are non-metals. So when they form ions, there was a gain of electrons. Whereas this one here is a metal, and there was a loss of electrons. So let's take a look at this next one over here. Here we have 11 protons and 10 electrons. So the atomic number right off the bat from the protons we know is 11, because the number of protons gives you the atomic number. And you'll notice that the protons and electrons, they don't, they're different. They're not the same. So this is not neutral. This is definitely an ion. And since the difference between them is 1, the protons are winning by 1, we know it's a 1 plus ion. It's a 1 plus ion. So we have to figure out what that is. Now, if you go in your periodic table to the atomic number, 11, that's sodium. So we have atomic mass is 23, I'm just rounding up, and then 11 for sodium for the atomic number. So we have sodium, 23, atomic number 11, but you need to put plus here to indicate that it's plus 1. You could put a 1, you don't have to. All the other numbers, you do have to write them in, but for 1, you could leave it out because we know you mean 1 when you put that. So you should be able to identify ions, number of protons, electrons, atomic number, and write standard atomic notations for neutral atoms, but also ions now, and symbols for ions as well. You should also be able to name ions. The metal ions keep the same name, so sodium becomes sodium, but the non-metal ions change their names. For example, chlorine becomes chloride when it becomes an ion. Remember, metals lose, non-metals gain. The whole purpose of doing this is to have a full valence shell at the end so that we can be stable. Essentially, these want to be like the noble gases. So that being said, why would something like neon be unlikely to form an ion? Why would neon not form an ion? So let's take a look at neon. I'm going to draw a quick Lewis dot structure for neon. If you look at neon over here in the periodic table, it's in group 18. So we know it's going to have 8 valence electrons based on what we're learning so far. So 1, 2, 3, 4, 5, 6, 7, 8. So this has a full valence shell. It's already stable. Therefore, already stable. So it's not likely to react. It's kind of unreactive. We call it inert because it already has a full valence shell. Which is why, again, something like neon, noble gases will typically not form ions. So remember that metals, as a summary, will lose electrons to become cations, and nonmetals will gain electrons, so I should say lose electrons, will gain electrons to become anions. And in doing this, they become more stable. These are more stable. And they're more like the noble gases, like noble gases. So a metal will lose electrons to become like a noble gas, and a non-metal will gain electrons to become like a noble gas. Let's go take a look at one more important point that will a trend or pattern that we might notice. So if you look at your periodic table, if you have a non-metal, like let's say oxygen, it's in group 16, 6 valence electrons, it needs to gain 2. It's going to gain 2 valence electrons, and it's going to become like neon, right? Because it has 8 electrons right now. When it gains 2, it's going to have 10 electrons total. Fluorine will gain 1 to become like neon. Nitrogen gains 3 to become like neon. Let's look at the next row. Fluorine gains 3 to become like argon. Sulfur gains 2 to become like argon. Chlorine gains 1 to become like argon. So the nonmetals, they tend to gain electrons to become like the noble gas that comes after them. Metals, on the other hand, will lose electrons. So, for example, sodium will lose an electron. It had 11, it lost one, and now it'll have 10 electrons like neon. Magnesium is in group 2. It's going to lose 2 electrons to become like neon. And then aluminum, group 13, has 3 valence electrons. It's going to lose 3 to become like neon. So metals lose electrons to become similar to the noble gas that came before them in the periodic table, right? Before, I mean like the smaller number up there. So let's just add that in there. So metals become like the noble gas before them, and non-metals become like the noble gas after them. When two elements have the same electron setup, the same electron configuration, we call them isoelectronic. So I'm going to add that term there. So for example, metal ions are isoelectronic to the noble gas before them. So for example, lithium plus 1 would be isoelectronic to helium. How did I know that? Lithium's over here. It will lose an electron to become like the noble gas before it, which is helium. You could say that bromine is isoelectronic to, you can try to guess before I say it. It wouldn't go all the way back here to become like argon, but it would become isoelectronic to krypton. It would gain 1 to become like krypton. So nonmetals are isoelectronic to the noble gas after them. So nonmetals are isoelectronic to the noble gas after them. For example, bromine -1 is isoelectronic to, let's go back to our periodic table just to show you again, is isoelectronic to the noble gas that comes right after it, which is krypton. So again, isoelectronic essentially means having the same electron setup or configuration to another substance. So metal ions, isoelectronic to the noble gas before them. Non-metal ions, isoelectronic to the noble gas that comes after them.